Our next speaker is Augustine Munagi, who will talk about the Bessenrodt-Ono inequality. Please.
Thank you very much. So I want to begin with the order of presentation. I will discuss the basic inequality with some definitions, and then I will state the compositions analog of this well, not exactly, but inspired by that, as we are going to see. Then we'll see how this can be applied to generation of compositions. And then there's a consequence of the previous work, construction of compositions. And then I will also carry out the same agenda for n-color compositions. A composition is any sequence of positive integers that sum to n. That's a composition of n. For example, there are 8 compositions of 4, and in contrast, there are 5 partitions of 4. There's the number of compositions of n has a very nice formula, which is equivalent to this recurrence relation. The partition inequality that inspired this work appeared in Annals of Combinatorics in 2016. It says that for any positive integers a, b, whose sum is greater than 8, that the number of partitions of the sum cannot exceed the product of the partitions of the two. Theorem 1 has been proved analytically and by using injections and inductions by several mathematicians, but not constructively. There are several references that could be given. For example, the attempt I made with some of my co-authors, 2017, Hem and Nauhauser, Gaj Zika, who spoke here today, have all done some wonderful work here. And in particular, the well-known two operations on partitions of multiset union and vector sum do not apply to help in proving this combinatorially. It's well known that these two have this De Morgan type relation where a prime denotes a conjugation of partitions. The composition case, it says here, if A, B are positive integers, then the composition, the number of compositions of A plus B is strictly greater than the number of compositions of A times the number of compositions of B. In fact, a more precise statement is possible. The proof is immediate. The numerical proof is immediate, as we can see. This is using the formula for compositions directly. It is split up, and we have this. The constructive proof is more insightful. To do that, we need the conjugates of a composition to understand it. If we have the zigzag graph of a composition, for example, this composition, its conjugate corresponds to reading the zigzag graph by columns. And another way of getting the conjugate is by algebraic, symbolic algebraic means. If we write a typical composition like this, that's in which the first part is 1, we have the conjugate in this form. For example, this is the composition which we put in this form, and then of course we can apply this rule to obtain the conjugate. We will use the following notations. Alpha and beta are typical compositions. We use the concatenation of two compositions. Okay, then we use the Cartesian product defined by concatenations in this form, where, of course, the last part of each composition is immediately followed by the first part of the concatenated one. For example, this is an example here. And we see that this composition of 3 and 5 become a composition of 8 in this form. And then this natural notation here, where the prime on a set means that every element is conjugated. The constructive proof is based on the fact that there is no self-conjugate composition of n if n is greater than 1. It simply means that any set of compositions can be decomposed into two disjoint sets, okay, where the second set consists of conjugates of members of the first set. And of course, that also means that we can always have this. Okay. So if we now apply this rule to the Cartesian product, we see that we have this. The cardinality will be the same as the set of conjugates, which will give you 1/2 of the whole set of compositions of A plus B, where, of course, we already know from the decomposition that the set is disjoint from the set of the conjugates. And this is actually what we wanted. Okay, this will give us exactly what we need, okay, because we now know that this is a disjoint union from this statement here, and that indeed the cardinalities are one and the same. This is illustrated in this table here. For example, these are the juxtapositions, and then the Cartesian product gives you this. Okay, then the conjugates, which can never overlap any element of the conjugates, appear here all distinct. So you find that the total number of compositions of 5 is given by all the compositions, the 8 compositions here, plus there are 8 conjugates. And that is actually the proof. But there are consequences to this, simple as it is. The set of compositions of n can be constructed from the sets of compositions of n1 and n2, okay, provided the sum. So this is the case of n equal to 2 of what is to come. In fact, it incorporates the original recurrence, the fundamental recurrence. But now the algorithm is accelerated if we choose the two n1 and n2 to be close to each other. But let's make it more effective. If we denote the right-hand side by this O plus, okay, let this be the notation we use for any two parts, then we find that it can be extended. It is actually an associative binary operation, so that in principle one can take as many parts of the composition as one needs. And of course, by induction, one can get this, and numerically also and obtain this. So what's the consequence of this? The set of all compositions of n can be constructed from the sets of compositions of the parts of any composition of n by means of applications of star and associativity. Okay? An example here, for example, if you want to get compositions of 7, you can decide to generate it by just this composition. Okay? Of course, associativity, we already saw how this was obtained, the 2 times the 3. Then we just attach this, and then we get the entire composition of 7. Okay? It can be accelerated further, and that is a doubling algorithm, so to speak. And this becomes quite efficient because you do not necessarily have to begin with a sequence of integers that sum to n. You begin with a seed sequence whose sum is less than n. Of course, if it's equal to n, we obtain the previous scenario. But it could be strictly less than n. And then when you get the number of compositions of the total weight, you now match that composition against itself and obtain another set. You continue doubling until you reach the weight, then the desired sequence of what you need for this computation will exclude n itself because n was already obtained. That is exactly how it works. And the interesting thing is that the only sets of compositions to be computed from scratch are just compositions of the seed sequence. Others are obtained by juxtaposition and conjugation, juxtaposition, or what I called concatenation and conjugation and so forth, recursively. And this can be programmed in a recursive computer algebra program. For example, let's take n here equal to 100. Okay, so with this expression, we can use any partition of 25 as a seed, say 10 and 15. And with it, using the procedure, we obtain this sequence beforehand, but we are only concerned with compositions of 10 and 15 to begin with. Once you obtain it, then you use what you got to get compositions of 50. So, and then use what you've got, total 50, to attach to this to give you 100. And you stop. Of course, if you had 200, you would have done it again. Okay, alternatively, one may use a composition of 25 into 3 parts, and obtain this sequence. If the number is odd, you just extract one. We've already seen that the case of n equal to 1 is almost trivial. Then it simply means you use 100, and at the end of the day, you attach O times 1. And this could be applied to even larger numbers. And you have a choice of what your seed sequence should be. Okay, and another construction of this, it does not really give you that same structure. However, it is a natural consequence of what we've just seen. A composition of n is called M-separable if M appears as one of the partial sums, okay, and M inseparable otherwise, okay. I have defined this as the join, where instead of just the concatenation, I've decided to add the last part of the first composition to the first part of the second. I called it join, maybe not a perfect terminology. A link would have been more appropriate, but it's fine for now. You can see that with this, we have a kind of De Morgan kind of relationship similar to the partitions case, but this is strictly for compositions. And this, looking at this and this properly, you will see that this lemma follows. A composition is M separable if and only if its conjugate is M inseparable. And with this, it means that the number of M separable compositions is actually independent of M. It's exactly 1/2 of the total number of compositions of N. Okay, so the construction is based on the following. This, the Cartesian product, union, just reversing, this is A, B, and this is C of B times C of A. And now this is the intersection. The first thing to notice here is that these two are disjoint. Okay, every element here is either A or B separable, and every element here is both A and B separable because of there's no conjugation here yet, just yet. So the separability is immediate. And is here, because if an element is here, it's either A or B separable, but if it is in the intersection, it is both A and B separable. Okay, so by the previous lemma, the conjugate of the intersections are neither A nor B separable. That establishes this. The consequence is that the difference here is exactly this conjugate. And our desired construction rule here now is this, where you have this union case and the conjugate of the intersections. These are just numerical values for verification if one were to actually construct and make sure that one gets exactly the same what one is intended to get. So the previous table takes this form, and as you can see, we have the same concatenations here. So this second and so this is A, B, and this is BA, 2, 3, and 3, 2. So the second and fourth columns give you this, but this intersection appear twice, okay? And therefore, one needs to replace one set of these intersections with their conjugates to get the complete set of compositions of 5. And that is what the construction is about. Lastly, we look at n-color compositions, which are compositions that come such that every part size M comes in M types or colors denoted by subscripts. And the number of n-color compositions of nu here is given by the F of 2 nu, that is the 2 nude Fibonacci number. This is an example of what it looks like. This is the same, exactly almost analogous to the case of ordinary compositions. The numerical proof also is straightforward because we can use this unknown identity for Fibonacci numbers, okay, which we blow up to be compatible with n-color compositions. And then if we translate this into n-color composition, we have something like this. So if you look at equation 3 with theorem 4, you will see immediately that it constitutes a numerical proof because this quantity is always greater than 0 whenever A and B are non-negative. I mean, whenever they are positive integers. Okay. The construction here, there is no consistent theory of conjugation of n-color compositions that applies to all objects. This is an established fact. From the works of Brian Hopkins, Collins, Dedrickson, myself. Of course, we know that this is true, at least from the previous case of ordinary compositions, that this n-color compositions of A plus B properly contains the Cartesian product, okay? But the difference is not given by the conjugate because of what I just said here, okay? Let's say but we have to go indirectly through ordinary compositions to how the n-color compositions are actually generated by the product of the parts of ordinary compositions. So if this is the set of n-color composition generated by an ordinary composition and you denote the cardinality by that, you find that the number of n-color composition generated by a fixed composition is given by the product of the parts of the composition. For example, you have this composition of 6. It generates these 6 n-color compositions by attaching colors. Of course, this function is completely multiplicative, but I won't talk much about it because of time. So at the end of the day, this is what we need, where our R is actually the set of n-color compositions generated by the set of ordinary compositions in the argument. And then this is the set of n-color composition generated by the conjugate. So you see that if the R and R were to drop, it gives us the ordinary compositions case. This is the best we can do. However, unlike the ordinary compositions case, the cardinalities are not the same. And the reason can be found from here, the relationship here between this concatenation here and its conjugate. Okay. In fact, the conjugate is usually greater okay, for reasons that is not really very hard to explain. So if you now express that this completely in terms of n-color compositions, it will give you this kind of recurrence relations, which of course reduces to the classical one by Agarwal, of course, if we set b equal to 1. But then this is the table, again, corresponding to all of that. However, obviously, there's no way we can list the number of n-color composition, list the actual compositions. But you can see that each number here is the product of the parts of the ordinary compositions that generate it. And these are the conjugates, and these are the product of the parts. And of course, all the formulas may now be verified because the total number of n-color compositions of 5 is the 10th Fibonacci number, which is the sum of this and that. And of course, the other terms also hold good. And so this is the little thing I wanted to share with you guys. I hope you like it. Thank you.
Thank you very much. Are there any questions for our speaker?
Hello, Augustine. It's Christian.
Hi, okay.
Thank you very much for a very nice talk. I have a
Great.
question concerning other inequalities for the composition or n-colored composition function. Have you
Yes.
considered like the concavity properties or maybe something? Because as far as I remember, for composition functions, we usually don't have the log concavity property. We do not have neither log concavity nor log convexity. I mean, when we consider composition of n where parts belong to a fixed set of positive integers.
Oh, yeah, those are interesting notions. And you can see that my viewpoint here is completely combinatorial, completely basic. And as you have already indicated, these inequalities, at least at this elementary base level, are not quite compatible with concavity. Okay, they are not compatible with concavity. However, I've not looked into that. It is something to look at. And given the depth that you have taken this notion, this inequality from your works, if you have something that you think is combinatorially challenging enough, you can throw it my way. We can do something, who knows? Well, thank you very much for the question.
Yeah, thank you very much. So maybe I will write you a message or an email.
Sure, thanks.
Thank you very much for a very nice talk.
Okay, thanks.
Any other questions for our speaker? If not, I thank Augustine again, and our next talk will be in about 5 minutes.
Thank you.
So if Lawrence can upload his slides, we will be ready to start soon.
Mm-hmm.